So it's my pleasure again to be here. And as Andrew already mentioned, the first session is about CCS. I start, but more interesting talks are coming after me. So that also is a spoiler alert. And today I am going not to talk about hydrogen. So that's the first news. And I'm going to talk about CCS, carbon capture and storage. And it's a big topic, obviously. And so to make it a bit more exciting and challenging for simulation science, I picked the fractured reservoirs as well. So we crack them, and then you would wonder why we would put CO2 in cracks deep underground. Yeah? So, and the story I'm going to tell you is about the learnings that we have had in the past 2-3 years. Yeah? And I'm going to share with you. Most of you might already have known it, but it's a confirmation that we learned it too. And if I remain any questions, I would be delighted if you please ask them. And I'm going to tone it a bit mathematical midway. If you want to check your emails, that's midway. That's the time for you to check emails. But I'm going to ask quizzes as well midway as well. Andrew mentioned mathematics of energy transition. And that's one of our challenges in universities, to tell even our own students and our colleagues that energy transition is more complex than we think it is. If we drive Tesla and we think we solve climate action problem, that's romantic perspective of the climate action. In Canada, we use more than 3,000 terawatt-hour energy, and that comes with more than 500 megatons of CO2 per year emission. Net zero goal, which we are not targeting on the track for, is expecting us at least to support the same amount of energy, if not more. See how warm it is here inside and how cold it is outside, and emit zero. This is mathematically magic, just as a matter of fact, right? We need to provide the energy, as a consequence, no emission. And so we have a lot of plans, a lot of scenarios. Carbon capture storage is one of the many topics in the picture, and it's being expected to reach between 3 to 10 gigatons a year. Andrew said 36 gigatons a year is the global emission, and we are targeting about 10% CCS. We have BECCS also, CCS itself, we have negative emission, they also need CCS, so about 10-15% CCS has to take care of. Hydrogen is the next, electrification the next, renewable and next. There are many, many. CCS is one. 3 to 10, to give you a feeling for it, we consume about 5 gigatons of oil globally. So we expect CCS business case be as big as oil industry. That's to give you a sense. How far we are? We are far from it. And my question is why? Why aren't we delivering something we have been working on for more than decades in universities at least? Yeah? And so Port Rotterdam, so that's my first quiz, managed to successfully cut emission by more than 30% in the past 6 years, from 30 megatons a year to 20 megatons a year. Why do you think, how do you think they managed to do this? Those who are in favor, raise your hands. First, electrification. I encourage our graduate students to please take a position. And my colleagues, watch them. Electrification, no one? Obviously, I wouldn't say the correct answer as the first option, right? They know already psychology of quizzes of professors. So, reducing on coal power plants. We are trying to decoal our energy mix. We are way from making sustainability a reality. And so that's why there are a lot of activities going around Europe, US, to actually target new real projects, because the question has changed, believe it or not. The question is not about whether CCS can deliver. It has changed. The question is, how can it deliver? How can we make it work? It's not about 100 ways that it doesn't work. It's about what's the one way that it can work. because this is our hope, that it's the only technology that can cut emissions by megaton per year scale. There is no other technology. There are some emotions attached to it when I meet with government officials. There are some societal perspective to this picture, and I'd be delighted to discuss that, but we have also a school afterwards as well. Now, to make it even more relevant, we do not have resource limitation. I could have put anybody, all the experts sitting here, their papers. This is one of our colleagues at MIT paper. We have our own self, but others as well have done this sort of capacity estimation. The global capacity is beyond 10,000 gigatons. It's massive. In Mount Simon, you can store more than 10 gigatons only. So it's not a matter of capacity or about reservoir. What is it about then? So I was asked in the annual visit by Duke, what's your dream? If you had enough resources or unlimited resources, most likely Energi Simulation is going to provide us unlimited resources soon with that 1 billion capacity of the market that I just observed. So if I had enough, 1 billion, what would I deliver? I would say my dream was to store 1 gigaton fluid under the ground. This scaling would make us believe it is possible. We need to show it to our kids that it is possible. And I have witnessed pure hydrogen being stored in gas field last year in Austria. And when I watched it, I believed it can work. So this is the confidence feeling we need to make in this market. So there is a geology aspect of it and reservoir aspect of it. I'm a reservoir engineer, so I put reservoir, but I mean geology. But it's beyond that. It's technical aspect, pipelines, wells, infrastructure. It's even more system economics. Who pays for it? And even beyond, it would be society. Who is going to license it? How are we going to monitor? Who is the liable authority after the commission is done? In California, Behnam, it's 100 years under the operator liability if they store anything on the ground. 100 years. So sometimes it's not reservoir simulation that doesn't work. It's just a license. Government, policymakers. I am going to talk about reservoir simulation, but the challenge might be somewhere else. How many of you think the challenge is technical side to deliver the technology? How many think one? Thank you for making some statistics. So how many think that the non-technical side is the major drive of the business case? Thanks a lot. That's a good thought for the school that Rick Chalaternig is chairing soon. So we need to look for all possible options, naturally, and select the best sites. Location, location, location matters a lot. And if you see carefully in that map, heavily faulted regions are avoided for capacity estimation. Yeah, we don't go to ask for trouble, right? So then we come to the simulation side and see how can we find a lifetime assessment for a CO2 when the CO2 molecule is going down in the earth and it starts to live. What will happen to this CO2? For some reason, we have been looking at this storage business in separate time-dependent process. Phase one is injection phase. When you inject the CO2, it starts, so injectivity is very important, pressurizing the reservoir is very important, clogging, all the matters of how big the pressure can be, what's the stream of CO2, all the matters go there. Then it's migration and post-migration where dissolution and the fingerings, all the things that we have simulated matter a lot. For some reason, we have done these classically in a separate, isolated time frames, because simulation powers and methods that we have been using in the past wouldn't have allowed for full cycle assessment. But we have done that. There are some mathematics behind that you would run the simulator and make it yourself that would allow you go through the entire life cycle and don't see it as separate phase of injection, migration, and post-migration, because believe it or not, migration of CO2 happens from day one. Dissolution of CO2 as well. The moment CO2 enters the reservoir and touches the brine, the sparkling water is made, or the champagne, whatever you call it. We have it from day one. And it's important to keep trace of all these elements from the right way in the scale of the time. And obviously, hysteresis, that when the CO2 is invading your reservoir or if it's leaving your reservoir, they also matter significantly. There are studies that field scale observations have been able to better match if you would make the relative permeabilities and petrophysical properties velocity dependent too, capillary number dependent too. Inshallah, reservoir could be better predicted when they did more advanced petrophysical properties. Yeah, I'm skipping that. And the other curve you see is the dissolution, how much CO2 goes inside the brine, and obviously based on different salinity that you have and different pressure, you have different dissolution, but CO2 lacks water. It gets into water. So dissolution is important. How about heterogeneity and fractures? That's the story. I hope this time is the time left for me and not, yeah, okay, excellent. Beside time, I have a multi-scale matter in a scale, in physical space too. And that's when we think about operating something at kilometer scale. We have a new project with Sebastian, with Petrobras. It's a reservoir which is 400 kilometers offshore Port Rio de Janeiro for CCS. We want to operate at several kilometers, and then the physics of a storage really takes place at microscale. And the whole challenge of heterogeneity, scale, and all the things is also related to my chair as subsurface storage and multi-scale modeling that I do at Delft. And one thing to note is also that to a large extent, the system of reservoir stays uncertain to us. I asked one of the new operators in Denmark that why did you choose this reservoir for your pilot test of CCS? And what was the answer? This is the reservoir I know the most about. I have the most data about. I know it the most. And then we as engineers will make it work. When we know what is it that we are dealing with, we will make it work. That's the power and strength of being a geoscientist, right? So you need to know what is the reservoir you're working on, and then you make it work. You find the way that it works, not 100 ways that it may not work. Yeah? And now adding fractures to this, I want to answer two questions. The first one, maybe you don't really have it, but I'm going to make it for you that you may want to care about, is how do we simulate them when the reservoirs are fractured? How can we do this explicitly, accounting for fractures at larger scale? And one other question, should you be happy if your reservoir is fractured? Is it a good thing that your reservoir is fractured, or it's something that you need to be careful about? The two questions, and hopefully you will have other questions. So it's not case site specific. So sorry for the acorn and also other field cases that will be also mentioned. I am talking more generic in this talk. So how do we deal with fractures? If you have a fractured reservoir for CCS, you have one major question before anything else. Where would the plume go? Would it reach unwanted zone? The rest of capacities, mixing, other things are secondary to you. The first question that you need to make it work is, where is this fracture network connected and taking my plume to? Is it somewhere I don't want to reach? Is there a legacy well there and I have no idea what I did 20 years ago to leave it? Then this is the main concern. So you need to know explicitly where the fractures are, major ones, and be able to treat them. So how do we treat them in simulator? We sat down and said, let's just dream. To have fractures that would be imposed on any given reservoir by any number and would not enforce you to change anything in your static model. You will have the same matrix grid, you will have the corner point grid, whatever you have in your reservoir, and you add fractures, and this way, even fractures that are added would not require anything for the previous fractures even. Everything is independent. It requires proper mathematics to consider these accurately, and especially the word that you see up is consistently. Consistency in simulation is the simulation would match exactly the physical world if the grid size is 0. The two are consistent. It is difficult to make it consistent, but it is possible. And others is about that you would like to have fractures. When I speak with geologists, Sebastian and others, fractures are heterogeneous. like matrix. They could be conductive, they could be barriers and seals. Giovanni, you might agree on it as well. So they could stop your flow. And this is difficult, to have a fracture and underlying or embedded on your system and stop the flow from happening in that overlapping grid. So we go to this test case. It's a heavily fractured system, and obviously you wouldn't need all of them to be explicitly considered because you are going to ask for trouble. You are uncertain about all these small fractures anyhow. So that's the concept of hierarchical fracture modeling that we have been working on for some years, that you detect the major one, and then you would homogenize or upscale the rest. But you keep some major fractures and cracks explicitly in the system, and we can debate until tomorrow about what's the cutoff scale. And based on what decision you make it, that this fracture should be homogenized, the other one should be explicit. That makes it a good geologist and a not so good geologist. You should have seen a picture of it. So then we do mathematical analysis of fractures crossing over you. And at the end of the day, with these methodology, you allow fractures to overlay the layer, so embedded on the system, and so far you are able to actually model it. There are transmissibility calculations that will be independently given to the system, and so at the end you will have something like this. Your reservoir is given the properties, your fracture properties are given, and you add them one by one on a given grid that you are given, and you do not change anything. And then it allows you, for example, solve this Norne field that is shown down there with a lot of fractures. And you can play with fractures, change one of them, or so nothing else is changed. Again, you run the simulator. A few of our learning. Now, that was the mathematics part of this. Now, in simulation, I showed last year that we did this fluid flower benchmark case with 12 universities, institutions, etc. Results were different. And sometimes results may look different. This is the solution of fingering of the fractures, the CO2. But effective dissolution of CO2 on this brine are the same. So if you calculate an upscaled effective dissolution that the two simulators are giving you, or two simulation methods are giving to you, they are exactly on top of each other. So you shouldn't be mistaken when the system is actually unstable in the simulation results anyhow. You shouldn't take it too seriously. Yeah? Find the effective parameters that matter to you. And if you go for analysis for hysteresis, the same thing. So you have with the hysteresis in the left, with no hysteresis on the right, and you see how it has impacted the migration of this CO2 and dissolution of it into the system. So these all matter. Petrophysical properties matter a lot. And what else? You have heard about Northern Light project, which is Johansen field. It's an aquifer. And when you inject CO2 in this reservoir, we got the public data. Data is public in Norway. So you can download it and work with it. And so we worked with it and said, what if the injection of CO2 is happening a little bit further? Injection 1, 2, and 3. They are in different locations. And you see, obviously, sensitivity to the plume migration when slightly your injection point is actually changing place. And then you may have plume going to the right or to the left with a slightly different location of at the end where the drill of the well is actually located. So what would you do? You simulate it, but then any simulator should allow for the first year surprises of your project. Allow for data integration and sensitivity analysis. That's the real thing in subsurface storage thing, because you haven't started anything, you don't have any production data for. You start this, and the first thing you do is that I need to have a simulator that takes the first year surprises of my field into account and tune itself. And that's the topic I believe that Sebastian may talk about tomorrow as well. Now to the fractures, the curious case of fractures. There are fractures that I said to you that you would like to know where the plume is migrated because of them, and then to know how much capacity the reservoir will have for you. The first set of fractures is that compared to the homogeneous case where no fractures exist, early after migration and long time after it, if fractures are highly conductive, you see if the fractures are very conductive, they are helping the mixing. They help the mixing and dissolution trapping of your CO2. So you should be very happy if fractures are conductive for you. If fractures are not conductive, they create untapped zones for the CO2 plume to go. they do not let the full capacity of your reservoir to be actually utilized for this. So for capacity estimation, it's extremely important to have a knowledge of these kind of barriers in your reservoir. As Sebastian puts it, tigers in the room. Yeah? A lot of other fractures can be homogenized, etc., but you would know the extent of the room, the plume migration with these. And then if you see the trapping, you see that the blue curve is the trapping of the highly conductive fractures because it enhanced the mixing of the injection into the reservoir, and so dissolution happened a lot better. And heterogeneity would do almost the same depending on the characteristics of your heterogeneity. So to come to the closing remark, explicit treatment of important fractures are extremely important, is very important, for you as the first step to know where the plume goes and does it reach my unwanted weak zones, legacy wells, faults, etc. The rest is mixing, and for that, capacity. If the fractures are highly conductive, they mix, they enhance the mixing of the system, it helps the storage. If they are not, then they create untapped zones, and then they don't let you reach those. And we are continuing on this. We just recently signed up a new project with the industry sponsors of this to actually advance it and then make it a commercial module for Chevron Schlumberger Intersect Alliance type of simulator. Yeah, and there are other, as I said, the offshore Brazil. We are going to simulate or model and anticipate migration of the plume in that aquifer. And the last remark I want to give you before I end my talk, I see Andrew about to kick me out, is that we asked them how much do we know about this aquifer. And they said the aquifer was between us and a gas field below. And we never looked at it. Now it's becoming very important because we want CCS to happen there. So we don't know a lot. And that's exactly what the magic is, to first know a bit about the reservoir and the key features and then help the CCS to take place. So this is going to make us busy for the coming 4 years with Sebastian. Thank you very much.
Thank you, Dr. Hadi Hajibeygi. Again, for the online audience, questions you can post online that I will answer or ask on your behalf. There are 2 microphones for people here. Just line up there to pose your questions. So I have 2 questions online for now while people are thinking about the questions here. The first one is, I have always wondered whether CO2 becomes liquid when it reaches the high pressure in the storage formation.
Yes.
That's from an anonymous attendee.
Yeah. Thank you, the anonymous attendee. So CO2 will be below 800 meter below the surface, it will be supercritical. And it will be really dense, like 700 kilogram per cubic meter would be the typical density you would have. But at the same time, it is very mobile. So it has the viscosity of gassy, not really gas, but it's quite mobile for a liquid type of thing. So we call it supercritical. It's not a phase, but it's a supercritical state that is quite heavy, 700, 600 kilogram per cubic meter, and then it is quite mobile, so it can really penetrate through the reservoir. And now there are some innovative ideas have happened some years ago. A colleague of mine who is a professor in Madrid, and at that time he was at MIT, Victor Villarrecia, he had actually this idea to actually store CO2 in liquid form, not in supercritical form. So that has been discussed also in the community, if we can change the state of it. And sometimes, the last point, is that we are concerned with gas fields about clogging near the well because of Joule-Thomson effect and the expansion, sudden expansion of the CO2 when it comes to the reservoir, it wants to expand, then the temperature drops, then hydrates form, and near wellbore is clogged. And some remedies for these would be to start to inject not fully at high pressurized, a bit maybe gaseous phase. There are discussions about hemodynamic state of that CO2 that would actually help us keep injectivity high at the beginning of the injection. But the rest is, most of the cases, we are talking about supercritical CO2 storage.
Okay, no questions here yet. The second question online is from Amadriza Shoje. How water-CO2 interaction is modeled in your simulation? Are they in equilibrium? I mean, when CO2 touches water, it dissolves instantly.
That's a great question. Yes, we are at the reservoir scale simulation, which assumes that we have for each grid block, one saturation, one value for relative permeability, whether imbibition or drainage. We've assumed fully mixed and instantaneous equilibrium in thermodynamic domain. So given pressure, temperature, we can do PVT instantaneously. Now, if you go to the reservoir scale simulation, for a reservoir of 400 kilometer, your grid size will be much bigger than this room. Now, is this a good assumption? Can we assume that this all tiles, everything is just homogeneous? We can have grid blocks of easily few meters by few meters for real field scale. But do we do them for challenging non-equilibrium thermodynamic? That's also another question. But for us, we assume instantaneous dissolution with the capacity that CO2 has from thermodynamic, from equation of a state. And what we do as benchmarking, and we have done this with the benchmarking of the CO2 when we participate, we benchmark our models, inputs, petrophysical or thermodynamics, based on experiments that are available. For CO2, we have a lot of experiments available.
Great. I really like this forum here, going global internationally, because this is almost like crowdsourcing. So here's a good question for you from, well, actually, it's quite a few already. Let me see. There was one on, yes, Rodrigo Castillo. Thank you for the interesting presentation. Do you think that CCS would benefit by adding chemicals such as surfactants?
Well, technically looking, yes, it might. Realistically looking, anything that makes CCS more expensive is better to be avoided. That's my realistic. If someone buys this, then yeah, make it. But I have doubt on it because of financial technical risks.
Okay. Question from one of our chairs from Brazil, Dennis. Got to turn the mic on. Okay, sorry.
Hi, Hadi. Nice presentation.
Thank you.
Thank you. For the simulation people like us, what do you think about the quality of the models, comparing our traditional models for modeling reservoir simulation for petroleum business and now for CCS? What do you think about the quality of the models, considering all these fractures and that you mentioned, and the whole of seismic 4D for monitoring this?
That's an excellent point. There are two things. Thanks a lot, Dennis, for this extremely well-thought question. The first is using old practice for new system. In oil and gas systems, we have been lucky that you drill a well and you get it out. It's already trapped there, and you get lively production data, that you have massive data that you can tune your simulator. So, and then seeing 2.5 kilometers under the ground, it's a lot of uncertainties there. The data is extremely valuable. So you would be able to tune your permeability, whether it is affected by fracture or not. You are able to tune it because you have a lot of data sets. For storage, we don't have much data set. In fact, we are going to start it and get the data as we start. So uncertainty sensitivities are a bit higher. In that case, we need to be careful, in my view, about the petrophysical properties that we put, at the same time about the quality of our upscaled reservoir representative quantities, including not just hydrodynamics, but also geomechanics as well, especially geomechanics. Because of fractures, I did not talk about geomechanics. Rick will talk about it later. It's quite challenging with the fractures to have also geomechanics, and that would also be a thing. So the data is very important, and that links to your second question. How do we incorporate data to our model? That is the monitoring side. And CCS, one of the bottlenecks for a CCS, successful CCS, is the cost of monitoring. When you start injecting, you don't want to leave the reservoir. You want to know after 100 years what will happen to your plume. Is it going on his way to reach out to the surface? That means, how are you going to monitor it? Any simulator should account for monitoring data, no question. But I think the next step is, and we are working on it, to see whether simulation and monitoring and geophysical monitoring can be connected so that the need for live monitoring would be less. And so you reduce the cost. Anything you do to reduce the cost of CCS, you will finally find someone to buy it. That's the message.